Now I want to talk about homeomorphisms, which are the kind of appropriate notion of isomorphisms between topological spaces. So definitions like this, let x and y be topological spaces, and then a homeomorphism from x to y is a function f from x to y such that firstly f is a bijection, which means that there's an inverse map, f inverse going from y to x, with f of f inverse of y is equal to y and f inverse of f of x. So that's for all y and y, and then this is for all x and x. Okay, so that's the first condition, that's got to be a bijection, and secondly, both f and f inverse are continuous. Okay, so we'll see examples later. It's this kind of, we definitely need both conditions here. Just because f is continuous, it doesn't imply that f inverse is continuous. F inverse is continuous doesn't imply that f is continuous. We need to check both those things separately. Okay, so that's what we mean by a homeomorphism. And we say x is homeomorphic to y if such f exists. And I'm going to write x, this kind of symbol here for to indicate that x is homeomorphic to y. Okay, so precise notation used for homeomorphism in different books. So I think I will try and stick to this particular symbol here. Okay, so examples. I want to claim there's a homeomorphism from any closed interval AB to any other closed interval CD, well, we need to define these maps F and G. I mean, typically, if you want to prove that two things are homeomorphic, you normally just have to produce the relevant maps. You have to produce the relevant maps F and G. I mean, there's not that many kind of abstract theorems that tell you that two spaces are homeomorphic without actually just doing the work of producing the homeomorphism. So that's what we have to do. So we need to find a function f from AB to CD, and we need to take the obvious one. There's this kind of graph here with a straight line. So here this is f of x. It's just a straight line graph that goes from AC to BD, so that's going to be A plus x minus A over B minus A times D minus C. And then we do the other way around. You've got your CD here, AB here, and we define G of x, or let's say call it y. So G of y is going to be A plus y minus C over D minus C times B minus A. Okay, so yeah, we should take these pictures here as just being kind of illustrative. This is our actual definition. and actually let's call these things f naught and g naught. So f naught is a function from the reals to the reals, and g naught is a function also from the reals to the reals. Okay, so we don't want functions from the reals to reals, we want functions from the relevant intervals. So, but let's just notice, so we've got d minus c over b minus a, that's going to be greater than 0. So f naught is strictly increasing. And similarly the other way around, b minus a over d minus c is g naught is going to be strictly increasing. And it's kind of clear that f naught of a, well, you put in x equals a here, then this go. I said this wrong, right? This should be c. Yeah, that should be c. That's correct. And then this one should be a. Okay, so f naught of a is going to be c. F naught of b, on the other hand, right? If you put x equal b in here, then you get b minus a over b minus a. That gives you a d minus c there, cancelling against the c, just gives you a d. Okay. So g naught, and similarly d naught of g is equal to b. Okay, so these things are all easy to check. And so because f naught is strictly increasing and takes these values here, so if a less than or equal to x less than or equal to b, then f naught of a less than or equal to f naught of x less than or equal to f naught of b, and then this one was c and this one was d. So f naught we can regard as, here I'm using the fact that these two inequalities, because f naught's increasing, and then f naught a is c, f naught b is d, which is from a formula like so. So we can see from this that f naught is a map from AB to CD, and similarly g naught, well, let's say it slightly differently. Therefore f naught sends AB into CD, so we can define f from AB to CD be the restriction of f naught. Similarly, you can define G from CD to AB a restriction of G naught, then simple algebra gives f naught composed with G naught is the identity from CD to CD, and G naught composed with f naught is the identity from AB to AB. So that means that and we should also mention here these are both clearly continuous. Okay, so we get f is a homeomorphism with f inverse equal to g. Okay, so so notice the kind of things we have to check here, right? We have to we have to produce a map from AB to CD, and we want to do this carefully, right? We want to produce a continuous map. So firstly, we define this f naught, and that's continuous map from the reals to the reals by standard kind of standard analysis stuff. And we do need to check, right, that it can be regarded as a map from AB to CD. We have to check that it sends everything in the interval AB into the interval CD, so that we can regard it as a map like that. And then similarly for G, and then we need to check composites both way around are the identities, and we didn't even bother to write that out. That's actually that's really the easy bit. It's more the kind of logical structure, making sure that everything is well defined and has the right domain and codomain, that's where the work has to go in. Okay, so that's proving that's what we need to say about closed intervals. We can also say similarly use the same formulae give homeomorphisms so AB's the doubly open intervals are homeomorphic, and similarly for half open intervals. However, these are all still finite intervals. We might ask about whether the infinite intervals are the same or different. And so we're going to prove, in fact, that the infinite intervals are homeomorphic to the finite intervals, but we're going to do that in slightly greater generality. So what we're going to do is going to consider, suppose n is, let's say, greater than 0. We're going to consider the full Euclidean space Rn and the open ball OBN, which, remember, that's the set of vectors x in Rn of norm less than 1. This is your normal Euclidean norm, the square root of the sum of the squares. Okay. So here I'm going to take n to be bigger than 0. In particular, n could be 1, and in that case, R of the n is just R. OB1 is just the finite open interval like that. So we'll be interested in that special case, but we're going to do it for general n. So I'm going to claim the formulae f of x is x divided by the square root of 1 minus the norm of x squared, and g of y is y divided by the square root of 1 plus the norm of y squared. They define continuous maps, f from OBN to Rn, and G from Rn to OBN. Okay, so I want to claim that these are homeomorphisms, inverse to each other. Well, the first thing to say, I mean, well, what's wrong with it? What about this formula f? We need to check that actually makes sense. So for x in OBN, we know that the norm x is less than 1, therefore 1 minus norm x all squared is strictly positive, therefore we take the square root of 1 minus norm x squared is well defined and greater than 0, therefore it's harmless to divide by it. Therefore the formula gives a well-defined continuous f from OBN to Rn. Okay? So that's this f. And then what about validating the formula for G? For y in Rn, well, the norm of y is greater than or equal to 0, therefore 1 plus norm y squared is greater than or equal to 1, and therefore certainly bigger than 0. Therefore, square root of 1 plus norm y squared is well defined and greater than 0, therefore harmless to divide again. So the formula gives a well defined continuous map G from Rn, but not yet immediately to OBN, right? We haven't checked what the norm of this is, but it's giving us at least a continuous map to Rn. Also, we know that the certainly the norm of y squared is going to be less than 1 plus the norm of y squared. So the norm of y is going to be less than the square root of 1 plus the norm y squared. So the norm of gy, remember the norm of y over the square root of 1 plus norm y squared, it's going to, so that's equal to the norm of y divided by the square root of 1 plus norm y squared. So that's going to be less than 1. So that means that gy is in OBN. So now we've got a continuous G from Rn to OBN. So let's go back to suppose that x is in OBN, and let's put y as f of x. So that's x divided by square root of 1 minus norm x all squared. So that means that the norm of y squared is going to be the norm of x squared over squaring this 1 minus the norm of x squared. 1 plus the norm of y squared, therefore putting it over a common denominator is going to be 1 over 1 minus the norm of x squared. So if we take g of y, okay, so that's y divided by the square root of 1 plus norm y squared. Okay, so then because you're dividing by the square root of that, that's y times the square root of 1 minus norm x squared. But then going back to the definition of what x was, right, that's just equal to x. But y, remember, was f of x, so g of f of x is equal to x. Okay. So I won't go through all the algebra for the other way around, but it's kind of similar. You find that f of g of y is equal to y. So g and f are inverse to each other. So we get homeomorphisms from OBN and Rn, between OBN and Rn. And so in particular in the case where n is 1, we get a homeomorphism between the open ball in R1, which is just the unit interval from -1 to 1. That's homeomorphic to the reals. Okay. And by restricting this, just looking at the positive parts here, you can check that the half open interval from 0 to 1 is homeomorphic to the half open interval from 0 to infinity. Okay, so that's an interesting homeomorphism. Actually, we can let's just explain that there's a kind of geometric interpretation of what's going on with those formulae. So here we are. Here's here's the unit interval from -1 to 1, and we've got some x here. Okay, and you want to know where is f of x. Okay, okay, so we've got f of x. Remember, was x divided by the square root of 1 minus x squared. In the one-dimensional, n-dimensional case, you'd say norm of x squared, but here we're just taking n equals 1, so it's just x divided by 1 minus the 1 minus x squared, and yeah, so you want to understand geometrically what's the meaning of this f of x. And what you have to do, you see, is you draw a kind of unit circle like this. Right? And now you've got your point x here, and then you lift it up onto the unit circle here. And then you draw out from the center from that point there on the unit circle, and you project back down onto the real line, and then it turns out this is f of x. Okay. I think I won't give the calculation here, but you can find it in the notes if you want. Okay, so that will be enough examples of homeomorphism just for the minute.